Hi everyone. In today's video, we are going to explore another crypto system called Hill Cipher. In this video, we are going to formally define what Hill Cipher is, and we're going to see a detailed example of Hill Cipher. Before delving into it further, there are certain concepts and topics that would be desirable if you're already familiar with them so we can get the most out of this video. These concepts are linear algebra, we're going to see matrix multiplication later on, modular arithmetic, GCD algorithm, given two integers, how can we find the GCD of those two numbers, and multiplicative inverse and finding a particular multiplicative inverse of an element in modulus M. Before giving the definition of Hill Cipher, we are going over a quick background of Hill Cipher and then we're going to see the definition. So here I'm going to give you a quick background of Hill Cipher. Hill Cipher was developed by Lester Hill in 1920s. Actually, Lester Hill is a mathematician, so it's not like Hill Cipher was named after Hill or it's related to a hill by any means. It is named after the mathematician Lester Hill. Hill Cipher used linear algebra. Hill cipher is somewhat similar to a fine cipher, except that Hill cipher is a block cipher and a fine cipher is not. It was introduced as an alternative to Wegener cipher. It was understood that it is more robust and harder to break. It is also an example of block cipher, just like Wegener cipher, as mentioned. So if you'd like to be familiar with a fine cipher or Wegener cipher, there are already videos for them that give you the explanation. If you like, you can go and have a look. And last but not least, it is important to note that Hill cipher is not a practical crypto system these days, and it is only used for historical and educational purposes. Using a modern computer that can be found in anyone's home or public libraries, you can easily break Hill cipher. So do not use Hill cipher for practical purposes. And with this in mind, now we're going to see the definition of Hill cipher. Much like any other crypto system, we are interested in a plaintext, ciphertext key, encryption function, and a decryption function. Now, with this in mind, let's see the definition of Hill cipher. We let n to be an integer greater or equal than 2. The reason that we are saying it's greater or equal than 2 is because if it is 1, then it's pretty much the same as a fine cipher. In a fine cipher, we are concerned with the equation ax plus b. If you set b is equal to 0 and let your n be the same as a, then they completely coincide. So just keep that in mind. Then we have our plaintext and ciphertext denoted by p and c, each having length n. That's how the concept of block cipher comes into play. We let the scripted looking K to be the set of all n by n invertible matrices over Z26, and we let K to be one of the members of this scripted letter K. Then we can encrypt our plaintext and get the ciphertext via the following equation. And lastly, we can decrypt this message and our ciphertext and get our plaintext back by the following equation, multiplying by the inverse of k this time on the right, and the formula for inverse matrix is displayed on the slide for your reference. We divide the aggregate matrix of k by the determinant of k to get the inverse of matrix K. There are some important implications of the definition that are worth taking our time and going over their details and see their implications. So as part of the definition of Hill cipher, we mentioned that we are interested in the n by n invertible matrices over Z26. it has two important implications. One is that it says we are interested in invertible matrices. Well, that may not be that surprising. That implies the determinant of the matrix K that we are interested in should not be 0. The second component that may not be that obvious is that it says we are interested in invertible matrices over Z26. So what that means is that not only the determinant should not be equal to 0, but also the GCD of the determinant number 26 must be equal to 1, or in other words, the determinant of this matrix K should not have any factor of 2 or 13 in its prime factorization, because they would share a prime factor with number 26. And maybe to get a better intuition, it's good to look at some non-examples. So the first one, we have this matrix M as defined with elements 3, 2, 6, and 4. We compute its determinant and we see it yields 0. That means that this is not an acceptable matrix. The second example, we have 22, 1, 14, and 5 as its elements. We compute the determinant this time. We do our calculation correctly, we get number 96. And note that the GCD of 96 and 26 is actually 2. It's not equal to 1. Therefore, again, this is an example or an instance of a matrix that is not allowed to be used in Hill Cipher. Now that we saw these important implications, we can get started with our example. For the example that we're going to see today, I have chosen the plaintext Hill Cipher and the key test. We're going to see how we can encrypt our plaintext using this key, and before doing that, we need to ensure that the key that we have chosen, which is the word test, is a permissible key in Hill Cipher. You can guess already that the key must be permissible. That's why it was chosen, but in general, it's a good practice to test whether the key is permissible in Hill Cipher or not, and we're going to make sure of that first before encrypting our plaintext. So the question that we're going to be asking ourselves at this moment is that whether the key satisfies the necessary requirements. So the key, once more, is the word test. First and foremost, we need to write it in the matrix and transform it into a corresponding value in mod 26. For doing that, we are going to use the mapping between English alphabet and numbers in mod 26. For this, we look at each entry in the matrix. First, we have letter T. We look at, we find letter T in our mapping. We see it corresponds to number 19, and we write it in the matrix and record it as 19, and we do the same process for every single element in this matrix. And we set it equal to K. We find the determinant of this matrix K, and I hope you're familiar with computing the determinant of a matrix. We get number 289. And then here we need to ask ourselves the two important questions, whether the determinant is equal to 0 or not. In this case, the determinant is equal to 289, which is not equal to 0. You have to make sure of that in mod 26. So 289 is not congruent to 0 mod 26. And it may not be obvious in the first glance, but 26 is an even number, 289 is an odd number. So there's a bit of reasoning in between, but once you've done that, you can be sure that 289 is not divisible by 26. And the second component is that we need to ensure that the GCD of this number, 289 and 26, is actually equal to 1. And it may not be obvious in the first glance, but 289 is 17 squared. And we know 17 doesn't cause any conflict with numbers 2 and 13. so we can be sure that their GCDs is equal to 1. So at this point, we are back to our initial setup with the difference that now we know that our key is a permissible key in Hill Cipher. Now the next step is to divide our plain text into blocks. We noted that our key, the word test, lead to a 2 by 2 matrix. So that means that we have to divide our plain text into blocks of 2 characters, which we can see right now. So we see, for example, that letter H in the first block, the very first letter corresponds to number 7, and we got this value by reading the mapping table between English alphabet and numbers in mod 26. For the purposes of demonstration, we are only going to focus on the very first block. We're gonna see the detailed calculation of how the encryption process can be carried out on the first block. We're gonna do the same process for every other block, but we're not gonna go through the details of those blocks. However, we're gonna see the encrypted values for those blocks. So if you like, at some point, you can pause the video and do the calculation for the remaining blocks before I show you the results. But for now, we're gonna focus on the first block. So at this stage, we are getting ready for our matrix multiplication. If you remember from the definition of Hill Cipher, in order to get the ciphertext, we need to multiply our plaintext by the key. So we transform our plaintext, the very first block, into a matrix, a 1 by 2 matrix, as you can see, 7 and 8, and we're gonna remind ourselves of the values that we got for our key, which is displayed here. And we are going to multiply these two matrices. And now we are going to see a detailed and step-by-step process of this matrix multiplication. So if you're familiar with matrix multiplication, you can fast forward this part, but just to remind yourself, we multiply this number 7 by 19 and 8 by 18 to get the first entry of the resultant matrix, and 7 by 4 and 8 by 19 to get the second entry. In the next step, we just simply carry out this multiplication for each one of these operations, and we get the following values. We sum them up, we get these values, and now the last step, we are interested in these values in mod 26. So we are interested in the value of 277 and 180 in mod 26. Again, this may not be obvious. It's completely fine to use a calculator to get these values, and if you do that, you see we have values 17 and 24. So what we have done so far, we multiplied the two matrices and we showed that the resulting matrix is another 1 by 2 matrix with values 17 and 24 in mod 26. And this is actually going to be our ciphertext. And we're gonna record these values in a new table, and we are going to look up their corresponding English letter by the mapping table as we've seen before. So letter R corresponds to number 17, and similarly 24 corresponds to letter Y, and that's how we get our ciphertext. So what we've done so far, we transformed our plaintext into blocks. On the very first block, we showed the details using our key, using matrix multiplication. We got the following matrix, 17 and 24. We recorded and find the corresponding English letters. And that is going to be our ciphertext, resulting ciphertext from the first block. Next, we are going to see the results for all the other blocks as mentioned in the previous slides for the plaintext Hill Cipher. So if you like, you can pause the video here and carry out the calculations and see what results you're gonna get, and then you can compare your results with the next slide. Here for your reference, I've included all the blocks and their corresponding values in mod 26. We've already done the process for the very first block, hi. Using the encryption function, we got letters R and Y. We do the same process for the second block and we get letters R and T. And if we carry out the same process for the third block, we get A, N, E, and similarly for the last two blocks, we get letters V, L, S, and B. So I hope you've gotten the correct results, or if you just wanted to skip and see the results, it makes sense to you. And now we are at the stage that we can get our ciphertext. So looking at the resulting ciphertext at each block, we can concatenate them, put them all together in one string, and get our ciphertext. And we're going to record it here. And it is given by the following letters, as you can see. So before moving on to the decryption component of the Hill Cipher, it would be nice if we give a quick summary of what we've done so far. So we started with our plain text Hill Cipher, divide them into blocks, use our key, the word test, use matrix multiplication on each single block and multiply it by our key. For each single block, we get a certain ciphertext, we put them together, and as you can see, we have our ciphertext at the bottom of the screen. So now our next step is to do the decryption of this ciphertext. So given the ciphertext that we see at the moment and the key that we have, how can we get our plain text back? So we're going to see that in the next step. We have our ciphertext and we have our key. So our goal is to use this key and use the ciphertext to decrypt the ciphertext and get a meaningful plain text, the same plain text that we started with initially. Before doing so, as you may remember from the definition of Hill Cipher, we need to find the inverse of our key. We know that the inverse matrix does exist because this is a permissible key, and we've shown this before. So now we need to find the exact value of that inverse matrix before we can move forward in our decryption. So for the next few parts, we are going to focus on finding the inverse. So we remind ourselves of the value of our matrix that we're working with, the matrix K, and we are interested in the inverse of this matrix in mod 26. The matrix is given, the inverse matrix is given by the inverse of the determinant times the adjugate of that matrix in mod 26. We've already calculated the determinant of this matrix before. That number is 289, which is congruent to 3 in mod 26. And the next step involves finding the multiplicative inverse of number 3 in mod 26. As you may remember, in the beginning of the video, I mentioned I assume that you know how to find the multiplicative inverse. In this case, it's not that hard to see. If we multiply 3 by 9, we get 27, and 27 is equal to 1 mod 26. So the inverse of the determinant is number 9. So we record that value on the left hand side of the screen. Now the next step is to find the adjugate of this matrix. Again, I hope you're familiar, but for 2 by 2 matrices, it is more or less straightforward. We need to interchange the position of the entries in the diagonal. In this case, they are equal, so we're still gonna write 19, and we just need to negate the values on the opposite diagonal. So we have we record -4 and -18, and that's how we get our adjugate matrix. So at this point, we have everything we need to calculate the inverse of the matrix K. We have the inverse of the determinant, and we have the adjugate matrix in mod 26. So simply we need to multiply the matrix, the adjugate matrix, by number 9. Once we do the multiplication, we get the following values, and we are interested in these values in mod 26. Again, using a calculator or a computer, we can simply find these values in mod 26 easily. And we see it yields the other matrix that we see with entries 15, 16, 20, and 15. And this is going to be the inverse matrix of K. If you want to convince yourself that this is actually true, you can simply multiply this matrix, the inverse matrix, by the matrix K, and it should lead to the identity matrix in mod 26. So now we've computed the inverse matrix and we are ready to continue the decryption of the ciphertext that we have using Hill Cipher. So we wanted to find the inverse matrix, the inverse of K, and we indeed find that matrix and we record it on the slide. And now we can use the same method that we use for encryption, that we transform our plaintext into blocks. We do the same thing with our ciphertext into blocks of 2 letters. The very first block, we have letters R and Y. They correspond to numbers 17 and 24 in mod 26 using our mapping table. We use the same idea for the remaining blocks and we record them here. And much like the encryption that we saw, we only focus on the very first block, and we're gonna see how we can use our inverse matrix and the values in this block to get the values of the very first block in our plain text. So we start with our matrix again. We have values 17 and 24, and we multiply it by the inverse matrix as before, using that's given by the definition of Hill Cipher, I must say. And once we multiply these values, again, I hope I'm going a little bit faster on this decryption component. So if you need to take your time, by all means, please pause the video, convince yourself that these are the correct values, and then we are interested in these values mod 26. And we get numbers 7 and 8, which is not that surprising. And we can see numbers 7 and 8 using our mapping table. They correspond to letters H and I respectively. So we record that in the table, and we saw that decrypting the first block, we get values 7 and 8, which correspond to letters H and I. We do the same process for the remaining blocks of our ciphertext, and we get the following values for the second block, third block, and for the 2 last blocks as well. Again, we can focus on the values, the letters that we get in each block. We concatenate all of these values and we get our plaintext. And it shouldn't be surprising that the plaintext is the word Hill Cipher again. So we are pretty much done with exploring our Hill Cipher, and I'm just going to give you a quick recap again what we've done for the decryption component, and that should be it for this video. So just to summarize what we've done for decryption, we started with our ciphertext. We assume that we don't have knowledge of our plaintext. That was the whole point. Of course, we know that the plaintext is Hill Cipher, but we're trying to retrieve that information. We use our key. So actually for decryption, we have to find the inverse of our key. We know the key has an inverse. This may not be the case all the time, so this is something that you need to check by finding the GCD and the determinant of the key. So then we use a block by block approach. We transform our ciphertext into block and multiply on the right hand side by the inverse of our key. For each block, we got certain plain text, and we concatenate them and put them together, and we got the phrase Hill Cipher back once again. So that was the plain text that we started with. Using encryption, we got the ciphertext, and using the encryption, using the ciphertext, we got the plain text back. And this is not that surprising that it worked well. That means that Hill Cipher, the algorithm for Hill Cipher works as expected. With this, I'd like to thank you for watching this video. I love to hear your comments, thoughts, or anything you'd like to see more of. And until next time, bye for now.